Hey everybody, and welcome to this video on shifting graphs up and down. So let's make it happen. All right, so here's the graph of the equation y equals 2x, and here are 5 ordered pairs both on the graph and in the table of values to the left. So what I'd like you to do is to quickly pause the video and please graph y minus 4 equals 2x and complete the table of values on the right. All right, probably the easiest way to graph this would be to put that equation into slope-intercept form. Of course, the graph is going to have the exact same slope of 2, that's why we have 2 parallel lines, but this new equation in red implies that our graph will have a y-intercept of 4 instead of a y-intercept of 0 like before. So it appears that replacing the y in our equation with a y minus 4 had the effect of giving our exact same graph but shifted up exactly 4 units. Now we did see this before, but I want to take a moment to delve a little deeper into the whys of why that just happened. Let's look at a few ordered pairs. For instance, for our original equation in blue, the ordered pair -2, -4. And let's think about how those would work when we substitute them in for our variables in this equation in blue. Of course, -4 is 2 times -2. It makes that equation true, that's why it's on our blue line. Now let's think of what happens if we try the same x value for this equation in red. The x value remains the same. 2 times -2 is still -4. But now, instead of y just being -4, we have y minus 4 is -4. Y now needs to be a lot larger in order to make this equation true. In fact, y needs to be 0 because 0 minus 4 is -4. And if we compare these two equations, in this equation in the red, that y value had to be 4 units bigger for the exact same x value to make the equation true. And hence, that point, -2, -4, went up 4 units to -2, 0. We'll do one more. In blue, the ordered pair 2, 4. Of course, 4 is 2 times 2. It works with this equation in blue, that's why it's on the line. But if we think about this equation in red, for the exact same x value, 2 times 2 is still going to be 4 right here, but it is no longer the case that y equals 4. Y minus 4 has to equal 4. Y's got to be bigger than 4. Y's got to be 8 in order to make this statement true. So for the exact same x value, the y value had to be 4 units larger to make the statement true. That's why we have the ordered pair 2, 8 in our graph in red. It's exactly 4 units higher than it was in our graph in blue. And that has happened across the board. That when we substitute the y in our equation with a y minus 4, it has the effect of taking our graph and shifting every single point up exactly 4 units. All right, let's try another. Here's the graph of y equals -3x. Of course, it has a slope of -3. The y-intercept is right on the origin, 0, 0. Now, why don't you take a moment to pause the video and please graph the new equation y plus 5 equals -3x. All right. Now, it was probably easiest to graph by putting the equation into slope-intercept form. Of course, this new graph in red will have the exact same slope of -3, that's why it's parallel, and it'll have a y-intercept of -5 now, and that's why this graph is exactly 5 units below the other. But I'd still like to go in a little bit more detail looking at some of these ordered pairs. For instance, the ordered pair in our original -2, 6. Of course, if we substitute those values in for their variables in y equals -3x, -3 times -2 is 6. That's why that point is on the graph. Now, if we look at this equation in red, if the x value is exactly the same, the -3 times -2 is still going to be 6. But y is not going to be equal to 6. Y plus 5 has to be equal to 6. That means y has got to be equal to 1. Of course, that's why the point -2, 1 is on this graph in red. But you see that the y value has to be 5 units smaller for the exact same x value. And that's why this point moved down 5 units to that one on our new graph. And in fact, that happened everywhere on the graph. Replacing the y in that equation with a y plus 5 had the effect of moving every point on that graph down 5 units. All right, so here's the graph of y equals 1/3 x. Of course, it's got a slope of 1/3. The y-intercept right now is 0. So why don't you take a moment to pause the video and please graph the new equation y minus 2 equals 1/3 x. All right, of course, it was probably easiest to put this in a slope-intercept form again. exact same slope, that's why they're parallel lines. Of course, this new equation has a y-intercept of 2, and that's why this line is exactly 2 units higher than the one before. For the exact same x value, the y value has to be 2 larger now, and hence y, replacing the y in y equals 1/3 x with a y minus 2 had the effect of shifting our graph up exactly 2 units. Alright, last example. Here we've got the graph of y equals 3/2 x. It's got a slope of 3/2. The y-intercept is right on the origin at 0, 0. But why don't you take a moment to pause the video and please graph the new equation, y plus 4 equals 3/2 x. Again, perhaps it was easiest to put this equation into y equals form, so you have the slope of 3/2, that's why they're parallel lines, exact same slope, but this time a y-intercept of -4, hence the graph has been shifted down exactly 4 units. So for the exact same x value, the y value is now 4 units smaller, and that's what takes all of these points and shifts them down exactly 4 units. Replacing the y in our equation with a y plus 4 had the effect of shifting our graph down by exactly 4 units. Alright, and now that we've explored a few examples, it's time to generalize our findings. So suppose that we have an equation involving x and y, or an independent variable and a dependent variable, and a graph that goes along with it. If we replace y in the original equation with a y minus k, where k is just going to be some number, this should shift the original graph up by k units. And if we were to replace the y in the original equation with y plus k, and again k is just some number, this should shift the original graph down by k units. Now note, so far we've explored this property using graphs that were all lines, but this property is going to hold for any equation and any graph, and we're going to look at a few examples right now. So here we've got the graph of y equals x squared minus 6x plus 7. Definitely not a line. Okay, well what happens if we replace the y in this equation with a y minus 2, and we want to graph y minus 2 equals x squared minus 6x plus 7. Not surprisingly, replacing the y with a y minus 2 has the effect of shifting our graph up exactly 2 units. Just find whatever points you can find on that graph and just move them up 2 units and you have your new graph y minus 2 equals x squared minus 6x plus 7. Alright, here's another example. Here in blue we've got the graph of y equals the absolute value of x minus 4 plus 2. But now if we want to graph y plus 6 equals the absolute value of x minus 4 plus 2, replacing the y with the y plus 6, not surprisingly, will have the effect of shifting our graph down exactly 6 units. Alright, last example. And here's a crazy equation and graph, the likes of which we've never seen before. X squared plus y squared equals 16. And what's interesting is the graph of that equation is actually a circle. So we've got this equation and a graph to go along with it. Now the question is, what happens if we want to graph x squared plus y plus 5 quantity squared equals 16? Well, replacing the y with the y plus 5, not surprisingly, will have the effect of taking our graph and shifting it down exactly 5 units. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.